So good evening and welcome. I am Nigella Hilgarth. I'm the Executive Director of the Birch Aquarium. I'm delighted to have you here tonight at the latest Jeffrey B. Graham Perspectives on Ocean Science lecture. And tonight it's my great pleasure to introduce our speaker, Dr. Jeff Severinghaus. Jeff is a professor of geosciences in the Geosciences Research Division here at Scripps Institution of Oceanography. He received his BA at Oberlin College in 1983 in geology, and his MBA at the University of California, Santa Barbara in 1988 in geology, and his PhD was at Columbia University in Lamont, and that was in July 1995 in geological sciences. And he has been a professor here since 2000. And he specializes in really looking at gases that are caught in ancient ice cores. And so that looking at these gases, you can have an idea of ancient climate and how climate has changed over huge periods of time, hundreds of thousands of years. And he is very well known in the field, has written a great many publications on the subject, has received numerous awards, also teaches a lot of courses here at Scripps. And really there is, I think, no one better to tell us the most up-to-date information that we can have about how climate is frozen in time, and these clues are some of the trapped gases in tiny bubbles in the ice. And so without any further ado, Jeff, I'd like you to come and tell us more.
As Nigella said, my main interest is in ice cores, and these are, as you may know, samples of the polar ice sheets from Greenland and Antarctica. And what is very special about these samples of ice is that in the polar regions, the snow that falls each year never melts. It's just too cold. And so it simply piles up and piles up and piles up. And ultimately, ice will flow, but that takes a long time. And so what we have in the polar regions is essentially a preserved record of time. As you go deeper into an ice sheet, you go back in time, and there are layers that correspond to annual layers, and these layers are perfectly preserved. And so just like counting rings in a tree, you can tell what time you're looking at by counting annual layers in an ice core. And so this gives us the power to say what was happening with the climate at a specific point in time in the past. And that's a very unique property of these particular ice cores. But even more unique is that as the snowflakes compact into glacial ice, not all of the air between the snowflakes gets squeezed out. A little bit of the air gets trapped, and that makes air bubbles. And so glacial ice is about 10% by volume air, and that is samples of the ancient atmosphere. And so we can find out what the gas composition of the atmosphere was in the past from looking at these little bubbles of air trapped in ice. And that's really truly unique. There's no other archive that works for preserving ancient samples of the atmosphere. So this has relevance to the ongoing global warming that's happening right now because of human fossil fuel burning. And the reason is that the ice cores are the only way we can tell what carbon dioxide has done in the past, and also other heat-trapping gases like methane and nitrous oxide. And so this allows us to ask the question, how have these gases changed in the past under natural influences before humans started to contribute to the change in these gases? And more fundamentally, what were the natural levels? We don't even know for these gases what their concentrations were before humans started changing them, because We only started measuring these gases in the 1960s or 1970s, and of course the industrial emissions of gases started 100 years earlier. So ice cores play a very unique role in helping us understand the background against which humans are changing the climate and changing the atmosphere, and help us understand what will happen in the future as humans continue to add gases to the atmosphere. So what I'm going to tell you about tonight are some of the things that we've learned from studying these ice cores. We've learned in particular that humans have driven the carbon dioxide concentration up 30% from natural levels, and that's something that only can be known from ice cores, because otherwise we wouldn't know what the natural level was. And we've also learned that climate can change very fast, naturally. This came as a real surprise. It used to be thought that ice ages came and went over many tens of thousands of years, with the subtle changes in the Earth's orbit that occur in those timescales, because the Earth's axis spins slightly on a sort of a 10,000-year timescale. And what's been learned from these ice cores is that climate can change much faster, in as little as a decade, from an ice age-like condition to a non-ice age-like condition. And these are natural changes, and they're not likely to happen anytime in the future, but it's very interesting to study them because it offers some clues about how the Earth system, how the climate system might respond to the push that humans are giving to it right now through adding greenhouse gases. So with that, I'll just launch in, and I'm going to try to make this fairly short so we have lots of time for questions afterwards. So this is obligatory at Scripps to show this picture. As you may know, Dr. Charles David Keeling, who recently passed away, unfortunately, started making this important measurement of carbon dioxide concentration in the atmosphere in 1957. If he hadn't done that, we probably wouldn't have learned about this phenomenon until several decades later. He was really ahead of his time. And what you see, of course, is the increase in CO2 due to human fossil fuel burning. And I should add that it's clear from the isotopes of CO2 that this has to be human-caused. And by isotopes, I mean carbon-13 as two different kinds of carbon. There's carbon-12, which is sort of ordinary carbon. Carbon-13 has one extra neutron in it, and carbon-13 is a rare isotope. And it turns out that the fossil fuels that humans are adding to the atmosphere are quite deficient in carbon-13 relative to natural CO2. And so we know that this rise is human-caused because of the carbon-13 in the atmosphere has been plunging over the same time period. So it's a smoking gun. So there's no argument about the fact that humans are the ones that are causing this upward trend. So that's the CO2 rise. The basics are that we've increased CO2 by 30%. We're going to increase it a lot more in the future. We've only just begun burning the fossil fuels. We can easily triple or quadruple the CO2 concentration in the atmosphere by just continuing our present economic practices. And we know it traps heat. So that's really the major part of the story. And since I brought it up, I might as well address the question, is the Earth warming? And yes, it is warming. There's lots of ups and downs because climate changes naturally as well as under human influence. So it's not a terribly simple story. But one question that I often get when I'm giving lectures is, how do we know that this is not just another natural cycle? And really the best evidence that this is not just a natural cycle comes from our basic knowledge of CO2 and other gases absorbing heat, and you can see that knowledge encapsulated in computer models that are shown in red. So the models here are shown in red, and then when we rerun the models without the CO2, without the greenhouse gases, we get the blue. And so you can see that repeated in different parts of the world as well as global. This is the global picture here. You can see that the models, when run without the greenhouse gases, pretty much stay flat. The black line is what's actually observed. So you see that the red band does a pretty good job of matching what's actually happening. And the blue band really doesn't at all. Apologize for the figure. This is from 1900 to 2000. So this is the whole last century, the 20th century. Now, why would we care about warming? Well, sea level will rise. That's one thing that's undeniably going to happen, because when you warm the planet, ice melts, and the tremendous amount of water is locked up in those polar ice sheets, about 200 feet worth. So if we lost all of the ice sheets, sea level would rise about 200 feet, and this is what the coastline of Florida would look like. One of the surprises that's been happening in the last 10 years or so is that many of these glaciers coming from Greenland and Antarctica are accelerating. And this was not anticipated by glaciologists, by people that study the ice. And so there are some big surprises and some major gaps in scientific understanding of how the ice will respond to warming. So all of these projections of future sea level rise should be taken with a big grain of salt. It may be faster than we thought. What I'm showing here is just the position of the edge of the fastest moving glacier on the planet. This is 1992, and it's been retreating rapidly till it's stuck right about here right now in 2007. And this is also not something that was predicted. So there's big surprises out there. And Greenland is melting faster, and it's also sliding into the sea faster than expected. This is one of the things that was not understood until recently, is that when you melt the surface of the ice during a hot summer day, it lubricates the bed of the glacier, and the water is flowing down a pipe called a moulin here, and the water reaches the bedrock, and it lubricates the base of the glacier, allowing the glacier to flow into the sea much faster than it was previously thought. So that's a surprise. So the result of all this is that Greenland is losing mass. This is a very clever way of measuring the actual total mass of the Greenland ice sheet using a pair of satellites called GRACE. This is the Gravity Recovery and Climate Experiment. And what this has done is actually measure the tug on the satellite from the mass of the Greenland ice sheet. And what it's found is that tug is getting less and less as the years go by. So the mass of Greenland is becoming smaller, and that has an equivalent of 0.6 millimeters per year. Just for reference, the sea level as a whole is rising 3 millimeters per year right now, and it's accelerating. It seems to be going faster with time. There's lots and lots of evidence that the planet is warming. This is the amount of frozen ground in million square kilometers. So this is, you can see that from 1900 to 2000, over the last century, there were changes in the area of frozen ground amounting to something like 2 million square kilometers. And the extent of glaciers, I apologize for the bad slide. This is, again, this 20th century, the positions of the ends of glaciers have been retreating. You can see that they're getting shorter. And if we look at specific places in Antarctica, we see similar kinds of patterns. This is the Larsen B ice shelf, which many of you may have seen before in the news. This is what it looked like in 2002, and then this is what it looked like 3 weeks later. This is a huge area, size of state of Rhode Island, that just broke up in a few weeks. And this was, again, not predicted. So there's lots of surprises out there. And so I want to emphasize that when you see projections of future sea level rise, it may be much higher. This is, just to give you an example, a prediction that was made in 2001, but actually it was from science that it was done in the late 90s, say 96, 97. And they estimated that sea level would rise like this with a range of scenarios. And then we actually are fortunate to have actually found out what happened here, so we can compare what actually happened with the prediction. What actually happened was this red arrow. This is from measuring the height of the ocean surface with satellites, and you can see that it's faster than all of these predictions. It's about rising more than 3 millimeters per year, whereas this is more like 2 millimeters a year. So now to just mention briefly that there are other gases I wanted to mention. I don't want to just focus on CO2. This is the amount of warming that's going to be due to CO2. Don't worry about the units, but this is just relative. CO2 amounts to about half of the expected cause of warming, and then methane is another little bit. Nitrous oxide, which is a laughing gas, you may know about that from your dentist. And then halocarbons, that's a very interesting one that's often not discussed. Halocarbons are the CFCs, those refrigerants and their replacements that are used for air conditioning and blowing foam and all kinds of things, firefighting. They have very long lifetimes in the atmosphere, and they are surprisingly effective at trapping heat despite very, very tiny concentrations. And so you see this whole red bar here is due to the halocarbons. So that's going to probably increase quite a lot. So it really is not just CO2. So I now want to switch or focus a little bit and talk about the ice cores. This is an ice core right here. It's taken with a drill. It looks like this. And the beauty of ice cores is that they're continuous. There's no gaps. You can get a continuous record of past climate up to 2 miles long. And as I mentioned before, there are bubbles. These are the air bubbles here. And then this is the CO2 that's from measuring those air bubbles from 1000 AD to the present, 2000 here. So that's the last 1,000 years. And this little blue band that you see right here, that's Dave Keeling's measurements. That's the Keeling era when CO2 was actually measured directly. So this whole time here is only known from the ice cores. And what you can see is that the CO2 concentration, which is here on this axis, is about 280 parts per million, and it was very stable throughout most of this period until about 1850. And that's, of course, the beginning of the Industrial Revolution, the time when large-scale burning of coal, oil, and natural gas started. And so CO2 started to rise about 1850. And this is the Keeling curve right here. And then this is the future. So these are various projections depending on economic scenarios. In other words, depending on how our economies grow, how the developing world industrializes, how people choose or do not choose to reduce their CO2 emissions, bury the CO2 underground, use alternative fuels, use alternative energy like solar or wind. So anyway, these are all different range of scenarios, but you see that all of them are going way up. So we've only just begun. We're going to go a lot farther than we have gone. And the Earth doesn't end at 2100, so this keeps on going. And so you see, we've got a long way to go. If we burned all the fossil fuels, we'd go up to something like 1,500 parts per million. We'd be up there somewhere. So there is real scope for a lot of increase. And so this is sort of one of the things that ice cores can tell us, that this is not something that happens naturally. It's pretty steady and stable naturally. Now, if we go back much farther in the past and we look over very, very long times, we do actually see subtle changes in CO2, but I don't want to mislead you here. These are very, very long times. This is the last 400,000 years. And then here's the present right here. And just for clarity, I've blown up the very last part of this graph. So this is a different scale right here than the rest of it. This is the last 100 years. So this is what you've seen before. And the CO2 is in the blue now. And so this rise is the rise under human influence. And then you can see that naturally CO2 does go up and down a little bit. It goes up to about 280 and down to about 200 or 190. It turns out that these fluctuations of CO2, which are quite slow, by the way, happening over thousands of years, these correspond to the ice ages. And this is a temperature record from the same ice core. And you see that when the temperature is warmer, CO2 is higher, and when temperature falls, CO2 falls. I also want to point out that methane in these same air bubbles in the ice core does very similar things. Methane tends to go down during cold times, during the ice ages, and up during warm times. So from this, we know that methane and CO2 help contribute to the ice ages. They're not the primary cause of the ice ages. The primary cause of the ice ages is, as I said before, changes in the Earth's axis, the spin axis. But there is an amplification that happens because of methane and CO2. And methane has been changed dramatically by humans. You notice that it's gone from about 700, which is the natural level, up to about 1,700 now. So it's almost tripled under human influence. And that's mostly because of agriculture, because of farming, cattle, to a lesser extent, rice agriculture. And then even longer in time, this is the longest ice core record that we currently have. This is 800,000 years. You see very much the same picture. Here's what I showed you before. CO2 is now in red. It's going up and down with these ice ages. Also nitrous oxide. There's incomplete data right now, but this is being filled in. And the same kind of picture emerges, that all three of these greenhouse gases tend to go down when the climate's cold, presumably because the climate is cold, though the details of that are still not completely understood. But then they turn around and add to the cooling by their heat trapping properties. And then if we go back even farther, there are no ice cores. This is the last 1.5 million years, and these are all these sawtooth ice ages that you saw in the previous graphs. And this is from a deep sea sediment core, and we don't have any ice cores that go back this far yet, though we're working on it. And we hope someday to get ice cores that go back all the way to 1.5 million years. And that would be very interesting, because you can notice that something was different back then. You notice that the ice ages came and went with a faster beat, and then they tended to slow down, and they got larger amplitude in this part of the record. So we'd like to understand, why that fundamental thing changed, and was it CO2? That was one of the hypotheses, is that atmospheric CO2 fell during this period, leading the Earth to get colder and into bigger and bigger ice ages. And so I'm part of a group that's working on that to try to drill the oldest possible ice core, and we're trying to drill in the very center of Antarctica, which is shown here. This is a topographic map of Antarctica. This is the high elevations are shown in the pink here, in pink and white. So the very summit of Antarctica is a place called Dome A, and we hope to get very, very old ice from there. Now I want to switch poles. This is Greenland, and in Greenland, there's a lot more snow that fall than in Antarctica, and typically annual layers that you find in an ice core are about an inch thick, so they're quite thick. And you can count them very clearly, so you have extremely good time information by just counting annual layers back to about 40,000 years. Beyond that, the record gets indistinct and you can't really do it. So starting in the 1990s, a series of deep ice cores were drilled at Greenland summit, which is right here. And these gave us our first really high-resolution records of climate. By high resolution, I mean annually resolved. So we could see what the temperature was doing every single year. And those records gave us a big surprise. They showed us that climate could change extremely quickly, as I said before. Just to show you what some of that ice looks like at the margin of the Greenland ice sheet where we've been working. This is some of the cold period ice, the Ice Age ice. And this is some of the warm period ice. And the transition between them is knife sharp. You can stick your finger on it. It's incredible. It seems to have happened in about 10 years. This is what the ice core data look like the last 15,000 years going forward this way. Here's the present. And the green line is the temperature that we have reconstructed from the ice. And I just want to point out that you do see some small fluctuations here. This little peak right there was a time when wine grapes were grown in England and the Vikings colonized Greenland. And then this little dip here is called the Little Ice Age, and that's the time when the Vikings all died out in Greenland. So you can see that humans were affected by these kinds of changes. And I've very cleverly blocked out this part of the graph. And now I'm going to show it to you. And you'll see that this is what the climate actually did well before humans were keeping written records, of course, but this is a big event. This is about 18 degrees Fahrenheit from here to here, and it happened in about 30 years. And about half of that, about 10 degrees Fahrenheit, happened in 1 year. So this is astonishing. This is something, again, not predicted by Earth scientists. You know, what could cause such a thing? And as I'll show you in a minute, this is not an isolated event. These things happen 23 times in the last 100,000 years. So they happen again and again and again. So there's something very important that's right at present is not very well understood about how Northern Hemisphere climate is regulated. And it very likely has something to do with the fact that when you get the ocean cold enough, you can freeze the ocean during winter. And that can't happen today. It's just way too warm today. So it's very unlikely that this is going to happen again, but it's a fascinating puzzle. I'm going to zoom in on this part right here in the last few minutes that I have remaining because it's a very instructive period. This is from 15,000 years ago to 10,000 years ago. This is a time when the great ice sheet that covered North America was melting back. It was melting back rather slowly. It took about 5,000 years to melt. But superimposed on that gradual melting, there were these abrupt climate change events. That's the one that I showed before, right there, that I said was 18 degrees Fahrenheit. Don't worry about the axes. Now the red line is from a sediment core in Venezuela. So this is not just Greenland, but apparently there's things that are happening in the tropics too. Probably not temperature, The temperature didn't change that much in the tropics, but the wind changed. And this is probably a record of wind, with strong winds happening when Greenland is cold and weak winds happening when Greenland is warm. And then I've superimposed on that last graph a third piece of information. That's the methane concentration from the bubbles in the ice core. And fascinating correlation is that when Greenland is warm, methane rises, and at the same time when Venezuela is not so windy. And conversely, when Venezuela is windy and Greenland is cold, atmospheric methane is low. So what does atmospheric methane tell us? Well, it turns out that methane is mostly made in swamps. Think of it as swamp gas, and rice farming today contributes a lot, but of course back then there wasn't a lot of rice farming, but there were natural swamps. And so basically methane is telling us something about the wetness of the planet, the wetness of the land surface. And so what this is telling us is that the land surface was much drier during the cold times, and then it abruptly got wetter when it warmed. So that's telling us something important about rainfall. And if you map out the places on the planet where it's wet, where methane is made, today you have a map like this, and the colors represent the swamps. Lots of swamps in the Amazon, to a lesser extent in the high Arctic. If you then go back to the last ice age, 20,000 years ago, here are the big ice sheets that cover North America and Scandinavia. And you see that there were still lots of methane sources in the tropics. So what this requires is that there was just a lot of the land was just drier. And that's relevant to our future, because this is a projection of what will happen in the next 100 years. This is sort of an average of the 20-year period from 2080 to 2099 of the change in rainfall that's expected with global warming. And this is one of those economic scenarios that's sort of middle of the road. It's not neither on the high end nor on the low end, but sort of right in the middle of the road. And what you see in the yellow colors are areas where it's going to get drier. Those are places where it already is relatively dry. So in other words, the subtropics, the desert areas, North Africa, South Africa, right in our own backyard here, we're going to be drying out. And so I think what the ice cores are telling us is that rainfall patterns did change and therefore can change very rapidly. And there could be some big surprises waiting for us in rainfall patterns in the next 100 years. And these models, by the way, the models that are used to make these projections, do not reproduce those fast changes. So whatever caused those fast changes, it's not in the models. So that's somewhat a cause for concern. And I'll show the whole 100,000-year record now from Greenland. Those are the two events that I talked about before. Now you can see there are 23 of these events. They all have numbers and names. And so they're not isolated events. It's something about the climate system that we don't understand yet. It may have something to do with the ocean circulation, possible that the ocean circulation can operate in more than one way, and it may flip between two different modes of operation quickly. But that's really a hypothesis. It's not actually known yet exactly what caused these events. So I think this is probably a good place for me to wrap up and take questions. Thank you very much. The question is, how do we get the temperature from the ice core? The way that has classically been used is that the ice itself has different isotopes of oxygen. Oxygen 18 is a heavy isotope, has 2 extra neutrons. Oxygen 16 is the ordinary kind of oxygen, and the ratio of those two is sensitive to temperature. The colder the temperature when the water precipitated, the less oxygen 18 you have. So that's sort of the classical way. Another way that we've developed here at Scripps uses the gases rather than the ice. And we use nitrogen gas and argon gas to get the temperature from the gases. And that turns out to be useful because then you can compare the timing of changes in gases like CO2 and methane directly with the changes in temperature. So the question was, how do we bring those ice cores back without having them melt or evaporate or losing the samples? Is that right? Yeah. Yeah, so the way we get the ice cores back to the laboratory without losing the air bubbles is by keeping the ice frozen. It's very difficult to do sometimes. You know, you can imagine that keeping something refrigerated all the way from Greenland back to the lab here in San Diego is quite a challenge. But turns out that with those blue ice packs that you may know about, blue ice that you keep your lunch cold with, those things can keep the ice cold enough so that the gas stays in the bubbles. And then once we're back in the lab, you know, we have a big freezer here, and we keep the ice at about -7 Fahrenheit. Well, the air is trapped naturally in the ice by the process of glacial ice formation. As the
How do you get it out? How do you buy it?
How do you liberate the bubble? We put the ice in a vacuum flask, evacuate all the modern air, the laboratory air, until there's nothing but a cube of ice and vacuum, and close the valve and melt it. And the melting releases the trapped air bubbles. Yeah.
How good a vacuum do you get?
Question is, how good a vacuum do we get? Well, we get to about 10 to the -4 torr, if that means anything to you. What is the diameter of an ice core? It's about 5 inches in diameter, about that big around. Yeah, the question was, is it true that East Antarctica, which is a very large body of ice, is also losing mass? And the answer is yes. Antarctica as a whole is losing mass, and we know that from that satellite that I mentioned, the GRACE satellite that measures the gravity. And as the gentleman mentioned, the reason that it's melting is a little bit different than in Greenland. Antarctica's quite cold. It's too cold for very much surface melting. Instead, the way that Antarctica is melting right now is that there are large areas where glacial ice floats over ocean water, and the ocean water is warming, and so it's melting it out from the bottom. And that's the main reason that Antarctica is actually losing mass right now. Question was, what's going to happen to Del Mar? Yeah. So my sister lives in the Bay Area, and she lives on one of those houseboats, and so she's always asking me, how much is sea level going to rise? And I tell her, well, you know, we don't really know. She said, oh, come on, tell me, you know. So I say, well, you know, if I really had to guess, between 2 and 6 feet in the next 100 years, something like that. And so it's probably somewhere in that range. And what that is going to do to Del Mar is not very much, because obviously most of Del Mar is way, way above that. So you're going to get some accelerated cliff erosion, because the power of the waves, the effect of the waves rather on cliff becomes much greater when you get just a little bit of a rise in sea level. So there's going to be accelerated cliff retreat, bluff retreat, but other than that, you know, not much effect on Del Mar. The question was, am I saying that the biggest impact of global warming on humans and ecosystems is drought? And the answer is yes. I think that's a point that's often missed. Most of us don't care that much about a few degrees rise in temperature, right? And just a summer to winter, you know, unless you happen to live in San Diego, there's almost, you know, we can all tolerate 3 degrees of warming. But the drought may be the biggest impact that we actually feel, because so many humans on the planet make their livelihood on natural rainfall patterns, especially in Africa and Asia, where you have these seasonal monsoons that a lot of people depend on for their livelihood. So I think, yes, drought is likely to be the single biggest impact of global warming. Yeah, so the question was that the temperatures do affect things like maple syrup production in Vermont because the sugar maple is moving northward. So Canada's going to get a sugar industry and Vermont's going to lose it. Yeah. So that's an interesting point. There's winners and losers. You see, it's not all bad news. Don't want you to go home with the impression that global warming is all bad news. There are shifts, and so it's important to be clear-eyed about all those different trade-offs. Lower heating bills in the north. Russians will be able to grow wheat. There's lots of positives too, but the balance is likely to be strongly on the negative side because there's so many more people living in the hotter, drier part of the world, and it's going to get hotter and drier, and relatively few people living in the cooler and wetter part of the world that will become more hospitable. The question was, when we look at the past record of ice ages that many hundreds of thousands of years ago, and the comings and goings of ice ages, is it the carbon dioxide that causes the ice age, or is it the tilt of the Earth's axis? As I said, and the primary cause is the tilt of the Earth's axis, and the carbon dioxide is an amplifier. Think of it as a feedback, as we say, and that means that it adds to the warming. It adds about 30% to the warming. In other words, if there were no change in carbon dioxide naturally because of the way the ocean, it's because the ocean warms up and the ocean outgasses some CO2 to the atmosphere, then the ice age temperature change would be about 30% less than it is. So about 30% of that warming is caused by the CO2. So CO2 is not the ultimate cause, but it is a proximate cause in the sense that it contributes something to those ice age changes. Just because climate has natural causes of change doesn't mean that humans can't also cause change. It's like saying that just because lightning can cause forest fires, that careless campers can't also cause forest fires. There's multiple causes, multiple possible causes. So the question was, how many core samples do we take for one area? And it's typically only one core, and it's about 2 miles long. So it's be a lot of extra work to take two, but that, in some cases we actually do that, and that happened sort of by accident in the case of the Greenland summit ice cores. The Europeans and the Americans were going to cooperate on drilling a single core, and they had a falling out. They didn't really get along, and so they ended up drilling 2 cores side by side. And it was a really good thing that they did, because it turned out that the bottom 10% of the ice cores completely disagreed with each other. Yeah, and we wouldn't have ever known that there was something wrong with the bottom of the cores unless we had 2 cores there. So I think the take-home lesson is very important. It's really good to drill 2 cores instead of 1. It turned out that the ice in the bottom 10% of the ice sheet was all scrambled up by ice flow. And so the record was no longer intact down there. So the question was, why don't we do it all in the other areas? And I think that we need to. In fact, what's happening now is we have about 7 different major coring projects in Antarctica, and all of those cores are going to be like checks against each other, because really the foundation of science is replication, being able to repeat something and verify that it's really true. It's a good question.